Welcome to Pomodoro Joe for Saturday, May 27th, 2023. Today we're doing LeetCode problem 1406, Stone Game 3. This is a hard problem. Alice and Bob continue their games with piles of stones. There are several stones arranged in a row, and each stone has an associated value, which is an integer given in the array stone value. Alice and Bob take turns, with Alice starting first. On each player's turn, that player can take 1, 2, or 3 stones from the first remaining stones in the row. The score of each player is the sum of the values of the stones taken. The score of each player is 0 initially. The objective of the game is to end with the highest score, and the winner is the player with the highest score. And there could be a tie. The game continues until all the stones have been taken. Assuming Alice and Bob play optimally, return Alice if Alice will win, return Bob if Bob will win, or return tie if they will end the game with the same score. Okay, so this is actually very similar to Stone Game 2. So if you saw that video, then this will be very familiar to you. So we will put 25 minutes on the Pomodoro timer and we'll get started. All right, so for this one, we'll build a recursive solution. So we have some Stone Game recurse here. And for this, we will need to know the index. So where are we starting at this point? So we'll take the index of our starting point. Then we'll go through. We'll see, we'll have a result, set it to 0 to begin with. We'll return the result at the end. All right. So now, with every recursive solution, we'll start with our base case. So if our index is out of range, that's greater than some max index, then we will return 0. All right, let's actually put our max index up here. That's just going to be the length of our stone value minus 1. That is our maximum index in the stone value array. All right, now with our base case out of the way, we can start going through our recursive cases. So let's see, for every I in range 3, so Alice can take 1, 2, or 3 of the stones. So we have 3 options here. So let's see, our current index. This is going to be the index that we pass in plus I. So that's the current index of the stone that we're looking at. And now she can take that stone and add to her points. So let's actually start out with some points up here. So these are the points of all the stones that she can take. So this is either the first stone at this index, or this first stone at this index plus the next stone at index plus 1, or the first stone and the second stone and the third stone all combined. All right, so our points will increase by the stone value at this index. And now we can recurse. So we have this option to recurse. So now we do our recursive call, passing in the new index. So it's Stone Game recurse with index or current index plus 1. All right, and now we run into our first problem. And this is solved in the previous video, so I won't go through too much of an explanation here, but the basic explanation is, so typically with a recursive function, you'll be saying, give me Alice's score, and it will return Alice's score. You'll grab some points, then you'll recurse, and it'll give you Alice's next possible score. But in this problem, we're actually taking turns. So this might be Alice's turn. She can grab a certain number of points, but this recursive call, well, that's Bob's turn. And so whatever we return from this call will be Bob's score. So we can't just take Alice's points and add the next round because that's Bob's points. All right, so the trick to this one is to actually use the total number of points in the game, then take Bob's score, subtract it from the total number of available points, and that will be Alice's score. So at this point, we'll have, let's see, our result. Well, that will be the maximum of either our current result, because we're trying to maximize our score, or the total number of stones, or total points, yeah, we'll call it points. Total number of points minus, this is Bob's score. I can call this Bob's score, I can call it op. I'm gonna call it op just because for the first call, this will be Bob's score. Then in the first recurse, that will be Bob's turn, which makes this return value Alice's score. Every time this changes, so this is actually your opponent's score. So we'll take the total points and subtract your opponent's best score for their next turn, and that'll be your result. And at the end, we do return our result. So this total points, where do we get this? So initially that total points will be all the points in the entire array. But for every subsequent call, we only take the points that are still available in the game. So that's going to be the total points minus however many points Alice took, or Bob took, whoever's turn this is. So we do actually need to pass in an additional argument to our function. This is remaining points. All right. So now that we have our remaining points, this is going to be the remaining points minus your opponent's score. But that does mean we also have to pass in another argument here. And that would just be the remaining points minus these points that you took. So you took some points, or I just called it, points. So you took some points here. You have to remove those from the game. So you take the remaining points, remove them, and then you do your recurse. All right, now finally out here, we need to make our initial recursive call, and we also need to format our output. It looks like we need to return Alice, Bob, or Ty, depending on who has more points. So we'll start with getting our total points. Well, that's going to be the sum of all the stone values. So we'll just do a sum of stone values. Okay. Next, we'll do Alice's points. That's going to be our initial recursive call here. So that's stone points, nope. So that'll be our stone game recurse, passing index 0 and the total points so far, which is all the total points. Next, we need Bob's points. Let's see, I'm going to separate these a little bit. So we have Alice's points and then we have Bob's points. So what are Bob's points at the end? Well, it's very similar to our recursive case here. Our Bob's points are just the total points minus Alice's points. So we'll do that. And then finally, we do need to format our output here. So we'll do if Alice points is greater than Bob points, then we'll return Alice. And if Bob point is greater than Alice points, let's do this one. And then finally, if neither of those are true, then there's a tie. So we'll return tie. All right, that's pretty straightforward. I'm just going to move these onto one line because they're pretty simple and it will clean things up a little bit here. There we go. All right, so it looks like that's it. We're going to have a recursive function, start our result at 0. I actually want to put this outside. Hang on. We'll put this out here so we don't have to calculate it new each time. So let's do that. That makes it easier. All right, now we'll go through with our recursive function. If we are out of bounds with our index, we'll just return 0. Great. Otherwise, we'll keep track of our points. We can take stones 1, 2, or 3. Well, we can take 1, 1, and 2, or 1, and 2, and 3. So we'll just keep track of all these points that we're grabbing. Then we'll do our recurse. Now, one thing I didn't check here, this index might be out of bounds. So let's do another check in here. So if our current index is greater than the maximum index, we'll just continue. We could return at this point, but we'll continue. All right, grab these points. Then we'll do a recursive call on the next available index and the remaining points to get our opponent's score. Then our score will be the maximum of our result, or these remaining points minus the opponent's score. All right, let's give this a try. Looks like I had a typo, of course. Oh, there's no S, it's just stone value. Try that again. And we pass. All right. Now, one thing I'll note. So this test case has a negative number. I didn't look at the constraints here. Yeah, so our stone values can be negative numbers. That could present a problem. So both of our scores, if all of these stone values are negative, both Bob and Alice could have negative points, but I set my initial result to 0, which means that this max will always give me at least 0. That's going to be a problem. So we need to actually set this to, I'll say negative infinity. You could set it to some very large negative number, but I'll use negative infinity or max negative value. Let's make sure this still works. All right, and one last thing we didn't do, which we can totally do, is we can use some caching to make this faster. We can use caching or we can use some type of memoization, but I will submit this as it is. If it doesn't work, we'll add cache and then we'll see how it goes. All right, time limit has exceeded, so we only beat 25 out of 185 cases, so caching might not actually be enough here, but let's give it a try. So we'll go back here, we'll add @cache, and I found out last time I don't need to actually import it, which is nice. So we'll add caching and see how this goes. All right, so that works. Let's see if we can pass all the runtime checks. And we pass, and we do okay. So we beat 33% for runtime and 7% for memory. Not great on the memory. All right, let's jump back here and I will show you another way to do this one. Okay, so with this, we are actually calculating Bob and Alice's score. We're finding their total scores and then we're comparing those scores. Now, one thing to note with this, we're not actually asked to return their scores. We just tell you who won, which means that we don't actually need to calculate their full scores. We just need to know their relative scores. And that's key to this next solution. So let's get rid of this. We don't need any of this. In fact, we don't need, yeah, we'll just keep our return value there. So for this solution, we'll be doing some dynamic programming. And the key to the dynamic programming is to recognize that we only need to have their relative points. We don't need to have their total points. So we'll have some DP. We're going to start out, these are all the possible answers for all the possible places. So the starting indices, if you start on an index, what is your best possible relative score? So we're going to start at 0. That's going to be multiplied by, let's see, we'll need at least, well, I'm going to change this from max index. Let's call this total stones or stone count. So we won't be subtracting this 1 here. We actually just want to know how many total stones there are. So we'll take this, multiply it by the stone count, and we'll add 1 because we actually want to start out being able to essentially grab a 0 from the past the end of our array here. So we're going to add 1 there. All right. So here's the basic outline. Before I start coding, here's the basic outline. At our given index, so we're going to start at some index, we can take the stones at that index, but that gives our opponent the option to take the best score they can get from the next index. So we're actually going to be starting from the end and working our way back to the beginning. So if we are at, some index I, well, that will be equal to the best option of the stones at this index minus, so we'll take the stones at this index, but then, so this is again relative. So our points will increase by this stone value, but our opponent's points will increase by the DP at I plus 1 because they get to take the next move. So they're going to take whatever the best score is for that next index. So again, this is relative. So our points will increase relatively by the value at stone at index I, but our opponent's points will increase by DP at I plus 1. So that's the best score for the next available index. But we don't have just one option. We can take the stone value at I. We can also take the stone value at I plus 1 or the stone value at I plus 2, pushing this one out as well. So our opponent will be able to take the next best value at I plus or DP I plus 1, I plus 2, I plus 3, etc. So that's our basic outline. So for this, we do actually need to go through our array backwards. So we'll have to say for every index in range, now we're going backwards. So we're going to end up at, well, let's see, we're going to start at the very end. So this is our starting point. Our starting point will be at stone count. Is that right? Stone count -1. We'll be going to 0, so we'll put -1 here because it's non-inclusive, so it will take us to 0. And we'll be going backwards, so we're taking steps of -1. Let's see, we might come back to this. I'm trying to think. If we start at stone count, this is inclusive. So we would start at basically just 1 past our index, our max index. But we want to be able to look ahead by at least 1 to get our 0 points, because at the very last index, you can take that stone and have some points. It's only at the last index plus 1 where you have your base case where you can't get any points. So we kind of want to keep that 1 extra, which means we don't want to start at stone count because that would be the maximum index. We want to start at stone count -1 so we can look ahead to that base case of 0 points. It's a little bit confusing. Okay. So now for every index, we have 3 options. Option 1 is we take this stone, and then our opponent gets the next valued, or the DP at I plus 1. So let's see. We can, yeah, I'll write this out as option 1, option 2, and option 3. So we have option 1. So our first option is we take the stones at this index. So we'll take stone value at this index, but then our opponent gets to take. So our relative score increases by stone value I, but our opponent's score increases by the next option, which is DP at I plus 1. So our relative score changes by increasing our score by this amount, but relative to our opponent, it goes down by this amount. Okay, so that's option 1. Option 2. Let's see. Well, this only works if we can do option 2. So we might have to do some bounds checks here. So we have to make sure. So if we're going to I plus 1 here. So let me maybe write that. All right. So if our index here is less than or equal to our stone count, then we can actually do this option. And our option here, option 2, that's going to be stone value at I and stone value at I plus 1. Let's see, let me grab these. So at this point, we'll be grabbing the stone value at this index plus the stone value at the next index. So I plus 1, or I'll call that index. But then we do need to subtract our opponent's next score. So again, our score will increase by both of these values, but our opponent's score will increase by, let's see, DP at I plus 2, because that's their next optional index. All right, and then finally, we have another index, that's I plus 2. And if this index is less than or equal to stone count, then option 3. This will be stone 1, 2, and 3. All right. And see, my index here has changed. So I might want to keep track of, like, for demonstration purposes, I am going to actually do this. This isn't the most efficient. We can clean this up in a minute. So we'll just say I plus 1, which means that our opponent goes I plus 2. We'll do I plus 1, and then we'll do another I plus 2. Let's copy this, add a plus here. There we go, I plus 2. So we can take the stones, this index, next index, and the third index, but then our opponent gets to go at I plus 3. All right, so these are our different options. Okay. Instead of calculating this index and using it here, I could just do this. Let's do that. It saves us 1 line, so let's do that. Okay, that cleans it up a little bit. But now we still need to see which one of these options is our best option. So right now I'm just calculating the options, but I'm not keeping track of which is our best option. So let's have some, this is like Alice's relative score, but I'll just call it score. Now we'll have to remember this is, okay, maybe I'll make a note here. Score starts at 0. They both have 0 points, so relatively their scores are 0 compared to each other. Neither one has the advantage. So positive score will be Alice, negative score will be Bob, and 0 is a tie. With our score here, we have to choose our best option. So again, this is for Alice since she starts first. So let's see our score. Well, I'm only creating these values inside my conditionals, so I actually probably have to do my checkout here. We can actually start score as the best option between the current score or option 1. We're looking for the maximum, right? So we'll say max of our current score or option 1. Okay. Oh, actually, hang on. No, we don't need to do this at all. We don't need to keep track of our score. We need to be updating our DP. Right. So this one is our DP at this index will start as option 1. But if we have a better option, then we can say DP at this index is equal to the max of DP at this index, or option 2. And same thing with option 3. All right. So now, at the very end, we're calculating all our DPs for all of the possible indices. What's the best possible outcome for each one of these indices? Now, I'm looking at max because we've defined Alice as being the positive value. So we're trying to make sure that Alice gets the best score, only because she goes first. She's the one who gets to make this decision. All right, so now this changes from Alice's points being greater than Bob's points. This changes to if DP at index 0, so this will be the very first move, which is Alice's move. If that is greater than 0, then Alice wins. If DP at 0 is less than 0, then Bob wins. So we have to say less than 0. Otherwise, it's a tie. All right. Okay, so let's just review this really quick. We were only looking at the relative scores between Alice and Bob. Now, with the relative scores between Alice and Bob, for every option, oh, we hit our Pomodoro already? All right, well, we are almost out of time, so I will wrap this up. Let's just see how this goes. Let's check this one out. All right, let's see. Oh, my index is out of range. Right, that should be a simple fix. We can just say if it's less than stone count, not less than or equal to stone count. Now, for less than stone count, we should be able to go I plus 2 because our stone count, we've actually added an extra one here at the end. All right, let's see if this works. I had the wrong type of parentheses. Man, I am just not doing well at all here. All right, if this doesn't work, we will break out some of these variables to make it a little bit clearer, but this should work. All right, and that does work. Let's see how we do. So this is not recursive, so it should be a lot faster than our previous solution. And it is a lot faster. So our previous solution, we had 33% for runtime, 7% for memory. This solution, we get a 93% for runtime and a 57% for memory. So we do a lot better. Now, there are a couple little things that we could tweak in here, like these maximums. These are always slow. It's an extra function call. So we can do something simple here, where dp of I will equal dp of I if dp at I is greater than option 2. Otherwise, it'll be option 2. Now, one thing we might want to do instead of doing this dpvi, because we'll have to be basically dereferencing, we'll have to grab these out of the index each time. We could keep a, this is what I like to do. I'll just do it here. So for every time through our loop here, we're going to have some best value. So let's see, our best score. It's going to start out as our option 1. Next, our best score will be equal to our best score if our best score is better than option 2. Otherwise, it'll be option 2. Same thing with option down here. Let me just grab this. Makes it easy. So we're replacing our max calls with this new maximum, our own internal like customized max calculation. And then we do need to set our dp at I equal to this best score at the end. Okay, let's give this a shot. Still works. Let's see if we can do a little bit better than our previous score. Oh, and we do. We get a 97% for runtime and a 53% for memory. That's a win. All right, that is it for me. This has been LeetCode problem 1406, Stone Game 3. We've gone through a couple different solutions here, one recursive, one iterative. Check it out. All right, hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.